everyone. Today we're going to talk about what's called the dot product. All right, so the dot product is an operation that you do with vectors, and it's very easy to define, it's very easy to compute, but it's also extremely fundamental to so much of math, physics, the universe, really. So this is a very important concept. So let's just write it down. So and there's a two-dimensional version and a three-dimensional version. So let's say A. If we have the vector A, which is say A1 comma A2, and B is the vector B1 comma B2, then A dot B, here's how we compute this. And so this right here, we put a little dot. This is called the dot product. A dot B is obtained by doing A1 times B1 plus A2 times B2. So you multiply the first entries of the vector, multiply the second entries of the vector, and add the results together. Right. Very easy to compute. That's called the dot product of the vectors A and B. And then if we have vectors with three entries, so let's say A is A1, A2, A3, and B is the vector B1, comma B2, comma B3, then we have the vector A dot B, and we're going to do the same thing here. Oh, I just said vector, sorry. We have the dot product A dot B, that's going to be A1 times B1 plus A2 times B2 plus A3 times B3. Multiply the corresponding components, add the results together, that's the dot product. And one thing that's important to notice here, you start off with two vectors, A and B, and in either of these cases, when you compute the dot product, the result is not a vector, right? The result is a number. So for example, let's say that A is the vector 4, 1, 2, and B is the vector 1, negative 1, 3. Then when we compute A dot B, we multiply the corresponding components and add them together, so it'll be 4 times 1 plus 1 times minus 1 plus 2 times 3, so that looks like 10 minus 1 looks like 9. So anytime we have a couple of vectors, there is this associated thing, this quantity called the dot product. And we'll see as we proceed why this is actually important, right? But you should just notice, it's very easy to compute. Now there's a few properties of the dot product. Let me put them here. So properties of the dot product. So the first one, if you do A dot A, right? So if you take some vector and take the dot product with itself, what you would get, so in the two-dimensional version, you get A1 squared plus A2 squared. In the three-dimensional version, A1 squared plus A2 squared plus A3 squared. This should sound familiar. This should remind you of magnitude or length, except with square root is missing. In fact, it turns out then, it should be easy to see, that A dot A is the length or magnitude squared of A. The second one, this is fairly obvious. If you do A dot B, that's the same as B dot A, so it doesn't matter what order you take a dot product in. Property 3, it satisfies sort of a distributive property. So if we do A dot B plus C, that's equal to A dot B plus A dot C. Property 4, you can slide constants around when you take dot product. So CA dot B, here we've got a scalar multiple of A, times the, or dotted with vector b, that's the same as c times a dot b, which is equal to a dot cb here. So notice c is a constant here. Up here it was a vector. Down here c is just some constant. So that's property 4. Property 5, the last one, if you do the 0 vector dotted with some vector a, so think about that, that would be 0 times a1 plus 0 times a2, if there's a third component, plus 0 times a3, what you'll get is 0. And notice on the left-hand side, this is the 0 vector, right? When you take a dot product, it's always 2 vectors. On the right-hand side, the result of taking a dot product is always a number. So this is the number 0 right there. That's the vector 0 right there. Okay, so now we're going to see, right, I mean, this is just sort of a computational thing so far, and now we want to see what the dot product tells us geometrically about vectors. So given non-zero vectors a and b, let theta be the angle between them. So you take your vectors, all right, there's a and there's b, and then you can measure the angle between the two vectors. Call that vector, or that angle, theta. So it turns out then, this is a theorem, it turns out that there's a relationship between the dot product and the angle between the two vectors. That's the geometric connection, right? There's this sort of algebraic computation, but it has geometric meaning for the vector. So a dot b is equal to the length of a times the length of b times the cosine of the angle in between them. So there's an important theorem. It tells us the connection between the dot product and the angle between two vectors. So as a quick sort of consequence, assuming that we've got non-zero vectors, yes. Yeah, never mind. A consequence, as long as you're not dividing by 0, then you have this, the cosine of theta is equal to a dot b divided by length of a times length of b. So, for example, let's compute the angle between, so my first vector is going to be a, which is going to be root 3 comma 1, and the second one root 3 comma 3. So we'll say and b is going to be root 3 comma 3. So if you were to draw these vectors, if you were to draw the position vectors of each of these, right? So it'd be kind of like this. There's a, that's root 3. So what does that mean? Go over root 3. So there's a, and then 1, 2, 3. Let me put it down here. And then vector b is up there. So we want to compute this angle right there. And to do so, we use this formula right here. So let's compute a dot b. That's going to be root 3 times root 3, which is 3, plus 3. So we get 6 for the dot product. The length of a, that's going to be the square root of 3 plus 1. So that's square root of 4, which is 2. And then the length of the vector b, that's going to be square root of 3 plus 9. So that's going to be square root of 12, which is 2 root 3. Let me just put it right up here. So now what we get is that the angle, or sorry, cosine of the angle between them is going to be a dot b, so that'll be a 6 in the numerator, and then we will have a 4 root 3 in the denominator. That's going to be why does this look so ugly? Let me just make sure I didn't screw something up here. Oh, yeah, okay, I got to clean things up a little bit. So let me multiply the top and the bottom by root 3. So that will give me a 6 root 3 over 12, which is root 3 over 2. Sorry, that looked ugly for a second. So now we get the cosine of theta equals root 3 over 2, and so that tells us that pi, theta is pi over 6. So that's the angle between those two vectors. Now, a piece of terminology here. So if the angle between two vectors, so let's say A and B, is pi over 2, then what we say is that A and B are orthogonal, right? Think of it as perpendicular, but the language that we use when we're talking about vectors, we say orthogonal. So then A and B are orthogonal, right? So orthogonal vectors, right, mean they meet at a right angle. So, okay, thinking back to here now, if the angle is pi over 2 on the left-hand side, cosine of pi over 2 is 0. That tells us then that the dot product has to be 0. So now we have that vectors A and B are orthogonal if and only if the dot product A dot B is equal to 0. So that gives us a nice, easy way to check whether check for orthogonality, right? So let's say theorem A and B are orthogonal if and only if A dot B equals 0. So, for example, let's look at this. So let's say A is the vector 1, 3, minus 1. And B is the vector 2, minus 1, minus 1. If we look at A dot B, that's going to be 2 minus 3 plus 1. So A dot B is equal to 0. So A and B are orthogonal. So remember this, the way to check for orthogonality between vectors, to compute the dot product. If you get 0, the answer is yes, they are orthogonal. This next thing we're going to talk about, this is especially important for physics, called projections. Now, here's the idea. I'm going to start off with a couple of vectors. In my notes here, I know I've been calling them A and B. In my notes, I call them U and V now. So rather than trying to adjust my notes as I go, I'm just going to switch to U and V. So here's the idea. Let's say, and I'm going to draw this picture kind of big. So here's a vector U. Here's a vector V. And imagine the sun shining down. If you drop a perpendicular from the tip of U down to V, I would like to know who the vector that you'd get if as the let's say the sun shining down, it casts a shadow. Who is the vector that is the shadow right there? Right, so that's sort of the idea behind there. So let's say it like this. Let's let W be the shadow that U casts onto V. This vector has a name. It's called the projection of U onto V. Right, so W is called the projection of U onto V, and it's denoted PROJ, and then there's a U here and then a subscript V, right? So this you would read projection of U onto V. Now, notice, so here's my vector W. W is a vector that points in the direction of V, right? And so what? Well, what it means then is that W is some scalar multiple of V. And so if I could figure out the length of W, that would be enough, right? Because then, so here's what we're going to do. If I can figure out the length of W, I know that then W is going to be a vector in the direction of V, whose length is exactly that amount right there. So that's the point. I need to know the length of W. So say it like this. So since W is in the direction of V, W will be, well, okay, it'll be a scalar multiple of V, which means it will also be a scalar multiple of the unit vector that points in the direction of V. And that's what we're going to do. So W will be a vector in the direction of V divided by length of V, the unit vector that points in the direction of V. So in fact, if we know the length of W, then all we need to do is multiply that length times this vector, and it'll tell us exactly who W is. So now, I need to do a little bit of trig here. So, length of W, that's equal to the length of U. So length of U times cosine of theta. All right, I've got a right triangle right here. Here's my angle theta. Well, I guess I should mention, so where theta is the angle between U and V. Right, I mean, all I'm doing here, cosine is adjacent over hypotenuse. Right? So cosine of theta equals length of w divided by length of u. Now, okay, so now what we have is length of u times cosine of theta is equal to, okay, so this will be length of u, and then remember our formula, cosine of theta is equal to u dot v divided by the length of u times the length of v. And so if you cancel, and remember that this is equal to the length of w, so now we have that the length of w is equal to u dot v divided by v. Sorry, not divided by v, divided by length of v. Okay, so now all I need to do is multiply this number times this vector right here. That will give me the projection. So what we have then is that the projection of u onto v is equal to length of u dot, not length of u, u dot v divided by length of v times v divided by length of v, right? It's a scalar multiple of that unit vector right there. The formula is usually written in a more compact form by joining up the stuff in the denominator there. So in final form, let's make sure I got this right. Oh, sorry, I forgot my absolute value bars right there. So the general form goes like this. Projection of u onto v is u dot v over length of v squared times v. This quantity right here also has a name. It's called the scalar component of u onto v. So let's write it out. So comp uv equals u dot v divided by v. This is called, this is the scalar component of u onto v. So we have two different formulas here, projection of u onto v and comp component of u onto v. Okay, so let's just try an example. So let's say u is 1, 2, and v is 3, 1. What I want to do, let's compute the projection of u onto v. So let's find, we'll do both the component of u onto v and the projection of u onto v. Okay, so first, for the component, okay, so that'll be the dot product in the numerator. So that's going to be a 3 plus 2, so we get a 5. And then we need the length of v. The length of v is going to be, let's see, 3 squared, that's 9, 10 square root. All right, so 5 over root 10. The projection of u onto v, that's going to be u dot v, which again is 5, divided by the length of v squared. Well, the length of v was root 10, so the length squared is 10, times the vector v, which is 3, 1. Oop, 3, 1. And so that's a 1/2 here, so that'll be a 3/2, 1/2. And let me just draw the pictures here. These things maybe are a little mysterious. Okay, so in the plane, if I draw the position vectors, I'm going to go over 1 and up 2. So there's my vector u. Then I'm going to go over 3 up 1. There's my vector v. So the projection of u onto v is that vector right there. So that's the projection. And then the component is its length. Right? I want to do one example from physics. So I don't really want to focus on the physics of this stuff, right? You can do that in your physics class. But let's just try one example to see where this comes from. So, before I do the example, so for a vector u, there's the horizontal and vertical components. So for a vector u, comp u vector I and comp u onto j, these are called, so these are the horizontal and vertical components. Of the vector u. You can think of them as the projections or the lengths of the projections of the vector u onto the x and y axes. And so oftentimes when you're doing physics, you would like to know the horizontal and vertical components of a particular vector. So here we go. A cannonball with muzzle velocity 200 meters per second. So that's like the initial velocity. So muzzle velocity 200 meters per second is fired at an angle of 30 degrees above horizontal. So it's fired at an angle of 30 degrees above horizontal. And what I want to do is find horizontal and vertical components of velocity. So find the horizontal and vertical components of velocity. So our velocity at exit, our muzzle velocity v, is going to be 200 times, okay, so there's the initial velocity, and then, right, so imagine this, we're firing the cannon like that, there's an angle of 30 degrees, and so it's going to be 200 times the vector cosine of 30, which is pi over 6, comma, sine pi over 6. And so what this is equal to, so cosine is root 3 over 2, so this will be 100 root 3, comma 100. Now, if you project this vector onto the x-axis, guess what you get right there? That's the horizontal component, and that one is the vertical. Okay, so that's a good place to stop. We'll see you next time.